Did it begin?
Should I start?
Hello?
Hello?
Stefanella?
Conseguimos ouvir.
Yes,
ouvir, Roberto.
Hildeberto, you start.
I think I have to click continue, right?
No, you can talk.
Okay, thank you. Well, it's a great pleasure for me to introduce Mark Levy. He's a professor from the mathematical department from the State University of Pennsylvania. And he works on mechanics, Hamiltonian systems. He has a great intuition for mechanical problem. He uses mathematics to understand physics, but on the other hand, also uses physics to give simple proofs, or at least to clarify some proofs, mathematical proofs, which might be more complicated through calculations. And he has published 3 books, one of them, The Mathematical Mechanic, which has a lot of examples of this reasoning. And I'm glad to announce to him at the course that he's going to give topics in Hamiltonian mechanics, And I'm glad to see him again in Brazil, this time remotely, but he has been here for twice in Recife, where he gave very nice courses on geometrical mechanics, and it's a pleasure to announce him for this course. Please, Mark.
Thank you very much, Hildeberto, for this very nice introduction. It's great to see you too. Again, I really enjoyed my visits. I probably would like to share my screen, but I don't know how to do it when I'm both on iPad. I don't know if...
You share your iPad. You can do from an iPad screen, share screen, and then start broadcasting. You have
how do I do that? I'm
share screen.
iPad. Should I probably go to Zoom?
No, you are already in a iPad. You go to the Zoom.
What if I just go share screen like
Yes.
this? Like this, share.
Yes, perfect.
And can you see now?
Yes.
Yes.
Is coming up. Still, did you click on what you want to share?
Yes, I clicked. I'm so sorry that
He was sharing, but then it's black.
It's for some reason. Let me. For some reason, it's black, right? I see my iPad, but.
Usually you do start broadcasting, share screen, start broadcasting. You have to press the button.
At least I make everybody else feel good about their technological abilities compared to
it's
mine.
No, it's that we use Zoom and actually
Don't worry, we are all in the same same level.
Actually,
let me stop share and I'll start again.
Yeah, so actually Jacqueline taught us, all of us, how to use Zoom and iPad.
For you to see the level that we have.
So
well, I think now it's
the trouble is that for some.
So usually when you share the screen, you have to start broadcasting as well on the iPad.
I never. What if I just go to my? What if I just go to? Maybe I will.
Because on the iPad, you share the screen and then you have to start broadcasting in order to actually, I don't know why it's too.
I will do the other way. I will simply go to this I will share screen again. Okay, now it works.
Yeah.
Okay, good, good. Well, after this horrible mess up on my
No,
part,
no, 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 no.
I
Don't
will
worry.
begin.
We are not in seminar, we are in school and we are in the classroom, so it's okay.
Well, in any case, if anybody is laughing, please.
No, no,
mute yourself.
no laughing.
So I don't know. I understand that the audience consists of mixed backgrounds. So I apologize if I am going to say things that everybody knows already, but I think it's a better choice than losing. So I would like to, in the first lecture, I would like to describe just a very quick run through the last, I guess, 200 years of mechanics, and to share my feeling that I never really understood some key things. Why do you do this? Why do you introduce, for example, the Hamiltonian? Where does it come from? Why is variational principle governing mechanics? I could prove things formally, but I didn't have this aha, this is kind of obvious, you would expect this. So the first lecture, I just want to not give these explanations, but just give the outline of this mechanics and point out the questions, which I'll answer in the second lecture. Okay, so, and again, I apologize for my maybe very elementary things, but I will start with Newton. And then 100 years goes by, and then I'm rounding off, and then Lagrange made absolutely amazing. And I think,
sorry, I think we cannot. I can see a white page. So if you wrote something, I can't see. At least me.
Oh, really?
Hmm.
Oh boy.
Maybe the color it's white. Maybe should change the color of the pencil.
You cannot see this, can you?
No.
Still
No.
not.
I'm so sorry. Let me re-share it again. Share screen.
We could see your page, the notes, but what you're writing, no. Now we can.
Yes.
Now you can.
Yes.
Okay.
Yes.
Great. Okay. So starting with Newton, I'll describe very quickly what everybody knows, of course, and then 100 years goes by, and then Lagrange. And then in about 50 years, Hamilton. So it's just the time between these discoveries, which I will describe, already says something about how probably difficult this thing is. And about 92 years later, Schrödinger's equation. So this is like a straight line leading from classical mechanics to quantum mechanics. And actually, I realized recently that this maybe the straight line goes from Archimedes, and that's kind of the point of the second lecture. Archimedes, about 2000 years. So this is a terrible gap between Archimedes and Newton. So, okay, so I want to give the maximally simple.
Galileo.
Yes, Galileo, of course, yes. Yeah. And I wanted to describe first, just to give the background. So the simplest system we're looking at is a particle in some force field. So the simplest case would be a particle on the line. Position of the particle is denoted by x, mass is m, and there is a force field acting on the particle. For example, maybe a spring that ties it to the origin or something like this. Then Newton said that mass times acceleration is equal to the force. The force depends on the position. And just to nail down the notation, dot means the derivative with respect to time, the standard notation. So 2 dots means the second derivative with respect to time. I apologize for, okay, so that's Newtonian mechanics. X can be a vector, so an example would be Kepler's problem. Then X belongs to the 3-dimensional space. And the force is, if we have the attracting center, let's say the sun at the origin, and the planet is at the position X, then the force is just minus points to the origin and inverse square. So then F is this, and Newton's law says this, that mx double dot equals to minus x over x cubed. So that's, by the way, there is an amazingly beautiful proof of Lagrange that these trajectories are ellipses, parabolas, or hyperbolas. It's almost, I cannot resist saying this. I don't know if probably many people, I have not seen it until several years ago. So
I will ask you the reference because I'm curious.
I'm sorry?
I will ask you the reference indeed. Maybe I will
Yes,
write to you.
I will be happy to give one.
Okay, thanks.
Yeah, so I can just give this amazingly quick proof that the trajectories are ellipses, parabolas, or hyperbolas. So here is the proof. If you call the distance from the planet to the sun r, r is a scalar, well, and the coordinates, let's say in the plane. We know that the orbits are in the plane, so let's forget the third dimension. So the coordinates of our planet are x and y. So this x here is the vector, but this x and y are scalars. Okay, so then the equations of motion, these are the only short formulas I write. It's minus 1 over r cubed times x, and the y coordinate satisfies the same, minus 1 over r cubed times y. And one thing that requires a tiny bit of calculation, which I'll skip, and that is that r itself, this distance, satisfies a similar equation if you subtract an appropriately chosen constant. So I will not do it, but that's the only calculation you need to make to show that it satisfies this same equation. So we have x and y and r minus a constant satisfying the same ordinary differential equation, which is w double dot equals to minus 1 over r cubed w. So I should clarify. Let's pick one orbit, and I don't yet know what that orbit is. Whatever it is, it gives r as a function of time. And so this coefficient here is some function of time I know nothing about and don't care at this moment. All I'm saying is that x, y, and r minus a constant satisfy this same linear ordinary differential equation. Well, then x and y are linearly independent solutions because I'm not looking at the straight motion. I'm looking at the motion with the non-zero angular momentum. So x over y is not a constant. That means x and y are linearly independent, and therefore any other solution is their combination. So in particular, r minus c is a combination with constant coefficients of x and y. And that's the proof. This is the equation of a quadric. with a focus at the origin, because r is just x squared plus y squared square root. And that's the proof. So the only thing I didn't prove is this formula, but that's very simple. It basically, you just say that the distance changes, I mean, it accelerates. There is a force pulling you into the origin, and there is a centrifugal force. And when you write that down, that's what this equation tells us. So it really is, I was amazed at how simple this proof is. Okay, so so that's Newton's law. And so 100 years goes by, and then, oh yes, maybe I should just mention that there is kinetic energy. We have to define energy conservation. I just wanted to point out energy conservation. So we have to define the energy. Before that, I have to define kinetic energy and potential energy. So what's kinetic energy? I mean, usually people say it's just mv squared over 2, but why? I just don't like any definition that I could ask, why not v cubed? Why over 2? Why half? So, so I can just maybe say that I think a better, pedagogically speaking, definition of kinetic energy, it's the work you have to, mechanical work you have to do to bring the mass from the rest to a velocity v. So it's the work to bring from rest to speed v. So this is the definition, and then a theorem, I mean, a very simple theorem. So theorem, I put it in quotes because it's so simple, but it's also very basic, that kinetic energy for a point mass equals to just mv squared over 2. And why is that so? Probably the best thing is to just say that by definition, kinetic energy is, so we start with a particle at rest and do something, and it acquires velocity speed v. And what's kinetic energy is, by definition, it's the integral from start time to end time. So this is time 0, and I don't know how long I do it. Hopefully it doesn't matter. And hopefully it doesn't matter how we accelerate it. All that matters as far as the work we spend is the final velocity and the starting velocity, which we choose to be 0. So, okay, so it's the force, which depends on time times the velocity, times means the dot product dt, right? Because velocity times dt is the infinitesimal displacement. So the dot product of the force with displacement is the work, right? So this is the definition. By Newton's law, instead of force, I can write ma, which is mass times acceleration. I don't write vector sign over letters. X is a vector, and velocity is the position dot, and this is the derivative by time of x dot squared over 2. And so we integrate the derivative, and so that's the increment. So it's 1/2 x dot squared from time 0 to time to the end time, and I forgot mass. Okay, so that's mv squared over 2. Okay, so kinetic energy is the work. What is the potential energy? Which we need to state the conservation of energy, to say that sum of kinetic and potential is 0. So, but to put every dot on every I probably should give the definition of the potential energy. And I saw in many books, it's kind of unsatisfactory. It just gives the formula and doesn't explain why. Again, I want to, so let's say we have a force field, think of gravitational field. So it's F, it may depend on the position. So I write F of X, it's a vector field. We have, let's pick a point, let's call it A. And I want to define the potential energy at the point X, let's say this is X tilde, the intermediate point. It's work by definition. It's the work, you see, again, we define it as work in the case of kinetic, and in the case potential, we also define it as work that I have to do against F. So if you think of F as gravity, it's the work I have to do to bring the particle from A to a given point against F to move the mass from A is an arbitrarily chosen but fixed point, to X. So potential energy at X. And to write it in formula, so potential energy V, we will call it V at X equals, so we pick a path, call it gamma sub X. So it starts at A, ends at X. It's the integral over gamma of the force dotted with dx. It's a bad notation, dx tilde. So x tilde is just a point that runs from A to X, and the F is evaluated at x tilde. And this is a dot product. So that's the definition of the potential energy. But one could ask, what if the path is different? Wouldn't the potential energy be different? Well, yes, in general. So we have to ask, so we only consider conservative vector fields, the ones for which the work does not depend on the path, which did somebody say something?
No, it's okay.
Okay, work is independent of the path. So what are the examples of the conservative vector fields? It's gravitational field is conservative. Unfortunately, it's a bad thing, because if it was not conservative, if the work along this path, for example, was, let's say, this work is small, and let's say this work was bigger, then we could have a free source of energy, right? We could drive our electric bicycle or a car up the hill along the easy path and go down the hard path, and we will end up with the battery charged at the end more than it was in the beginning. So we could sell this surplus electricity and keep doing it and get a free lunch. But so in other words, the fact that gravitational field is conservative is a restatement. It's a special case of the fact that there is no free lunch. The same applies to electrostatic field, but some force fields are not conservative, and actually it's kind of a nice thing. For instance, the vector field, the velocity field above the sea, let's say, it's fast higher up and slower near the surface. And in this case, one can extract, well, it's not a force field, it's a vector field, but if you look at the object, if you place object at rest in this vector field, then it feels this force. So this velocity field is related. You can interpret it as a force field. And here it's not conservative. For example, you can take a path like this. And a bird's, for example, you can go this way perpendicular to the force, then you do no work. Then the work is done for you because you're going with the force. Again, no work, and again, no work because force is zero. So we end up having work done for us. And actually, birds extract, some birds soar like this. They can, without updrafts, they can fly forever in theory by extracting energy from this wind. Also, there is a nice video on YouTube, downwind faster than the wind. It's about the same kind of thing when similar thing. When the wind blows, can you sail faster than the wind going straight with the wind? So, of course, with a regular sailboat, you cannot do it. You can go just a little slower than the wind. But if you are allowed to do some kind of mechanical gears, no source of energy, then you can actually go faster than the wind, downwind. And in theory, without going into details, how you implement it, in theory, it should be possible because you have two media, you have the ground and you have the air, and they're moving relative to each other. So in principle, you should be able to harvest this energy. It's kind of a non-conservative, well, it's not a vector field, but anyway, so that's kind of a nice thing. You can just Google it and see on YouTube, unless you already did. Okay, so
what's the name of the video?
Yeah, it's downwind faster than the wind.
Thank you.
Actually, I have also a small explanation on my website. There is a little article from SIAM News. You can look, it's very quick. It's much quicker than watching the YouTube, but much less entertaining also. In that YouTube, there is a physics professor who I feel so sorry for. He kind of claims that it's impossible to do and eventually had to admit that he was wrong, but to do it in public, it's so horribly embarrassing. But he was amazingly gracious. Okay, so we define two energies. We define the kinetic energy as the work we have to spend on moving thing, and potential energy is the work we have to spend on raising the thing, so to speak. And maybe just a quick example. So if we have the gravitational field, just mg, the force acting on a mass, then if we start from the point on the ground and move it at the distance h and compute the work along any path, we'll find mg times h. So it's clear that the product of the distance in the force is this, the distance. And because the work doesn't depend on the path, it's, I'm sorry, I'm doing it a little fast or maybe too slow. Another example is in the gravitational field of the sun. Let's say here is the sun at the origin, and the distance to the sun is r. How much work do we have to do to bring the mass from, well, we have to pick the initial point. If we pick the sun as the initial point, it takes infinite work, it turns out. I mean, if we treat the sun as a point mass. So infinity is the next natural choice. So if we integrate the force, which is 1 over the distance, call it x, from r to infinity. So if I, that's, sorry, the force is 1 over x squared, right? So it's 1 over r, but that's going the wrong way. The work is, you have to start at the chosen point and go to the location in question. I did the opposite. So the actual answer is going to be minus 1 over r. So the potential energy, the graph of the potential energy is this funnel. Okay, so these are two examples of potential energy. So the conservation of energy. I apologize if everybody knows this, but I thought maybe I'll describe all these things, and then next time I want to show what an amazing thing that a totally different point of view that is, I guess, basically due to these Lagrange Hamilton Poincaré. I should have mentioned Poincaré here, of course. How all these things look totally different from another point of view. Okay, so here, conservation of energy just for this particle in the gravitational field. I should have said that we define the potential energy, and how is the force related to the potential energy? Well, here is the relation, here is the energy, here is the force, but, oh, I'm so sorry. I made a huge, I said against, I even wrote it fatter, but I didn't put the minus here, because if I am taking the particle from A to X, I have to apply the force to compensate the gravity, so to speak, right? So I have to apply the force minus F. The emphasis is on I have to do this work. So I am applying the force which is minus the ambient force, so that the particle is basically in the quasi-static equilibrium. And then it takes the nudge of a mosquito to just move it, right? So basically the work I have to do, if one doesn't like this sentence, this is a precise definition, but I wanted to motivate the minus, and the minus is due to the fact that I have to apply force opposite to the ambient force to be able to move the thing. Well, slightly greater force, but arbitrarily close, and so in the limits. So anyway, so that's the relationship between the force and the potential energy, or if we take the gradient of both sides, then we say that the force is minus the gradient of the potential energy. Okay, and now we can write Newton's law is, instead of force, I write minus gradient of the potential energy, that is force. Okay, now conservation of energy, how do we, instead of proving it and stating it, I'll derive it. So how does one derive conservation of energy? One multiply both sides in the sense of the dot product by the velocity. And then we get mx double dot product with x dot, and minus gradient dotted with the velocity. Why do we multiply by velocity? Well, because if this is the force and we multiply the force by the velocity, we compute the power, right? If infinitesimal force times infinitesimal displacement is work. If it's in rate x dot, then it's work per unit time, so it's power. So basically, we're already getting something that says about work by taking the dot product with the velocity. And this is, we recognize this as the time derivative of m velocity squared over 2, squared in the sense of the dot product. And that's, by the chain rule, we recognize the time derivative of v of x. X is, of course, a function of time. I don't write it. And so therefore, we get the kinetic, the total energy is a constant along the solutions. So this is a constant for any solution of the Newton's ODE for any motion. So it doesn't depend on time. For different motions, it's different, of course, but for each motion, it doesn't change with time. Okay, so this was all I wanted to say about Newton's formulation. Then 100 years goes by and Lagrange made this amazing discovery, which I think is kind of underrated. I find it more impressive than coming up with Newton's law. Maybe I'm wrong, but that's just sharing my feeling. Okay, so for whatever reason, and this is one of the questions that I've not seen any book address except for one, and maybe I'll mention very quickly. So you define the Lagrangian, consider the difference of kinetic energy and the potential energy. I'm still talking about a particle in space. It could be much more general. It could, for example, be a pendulum with 2 legs or more. But just to be specific, so in our case, it would be mv squared or mx dot squared over 2 minus the potential energy V of x. So why difference? That's strange, right? So this is a function of 2 variables of x and x dot. And of course, x and x dot depend on time, but right now I'm treating them as independent variables. So maybe I should not even have called x dot, but said v or something. So right now we're not thinking of them as depending on time. And let's just compute. So this is one function which encodes all the information about the mechanical system. So for example, if we differentiate L with respect to x, what do we get? X and x dot are independent of each other. They're just independent variables. So L sub x is just minus v prime, right? Or if it's if x is an Rn, it's minus gradient of v. And L differentiated with respect to x dot equals to mv or mx dot. So this is the force, and this is the momentum. I don't know, in Russian, the word for momentum is a little bit more descriptive. It says the amount of motion, which is kind of a good name for it, I think. I wish it was the same in English. The amount of motion is much more accurate than momentum, I think. Well, maybe if one knows Latin better than me, then it's... Okay, and then Lagrange's discovery was twofold. Well, one thing is Newton's equation is equivalent to the following equation. You take the derivative of L with respect to x dot, and then, so you see, when you do this differentiation, this is a little bit weird. You treat x and x dot as independent variables, but then you take the derivative with respect to time. The moment you write this derivative, now you switched your thinking. So this is a little confusing. When you write the derivative, you switch, and now at that moment you treat x and x dot as functions of time, but not before. And subtract from this L differentiated with respect to x. This is the equation that's equivalent to Newton's equation, but it has a tremendous advantage over Newton's equation because this method of getting the equation of motion works even if you don't use, for example, for a particle in polar coordinates, it's the same thing. X and x dot don't have to be Cartesian coordinates in the approach of Lagrange. In Newton, they have to be, but for Lagrange, you can take any variables you like, spherical coordinates for a particle in the sphere, or for a say a pendulum with 2 legs, a double pendulum like this, or triple. You can take, for x, you can take these angles. So this can be x1, x2, x3. and then x is the vector of these three variables. You can write down kinetic energy, potential energy. That's a geometrical problem for this, and just plug these into this equation. It will be three equations, right? Because x is three-dimensional, so it will be gradient of L with respect to x, so three vector. This is three vectors, so it's three equations. So it's a tremendous advantage in practice. That's what all engineers, I guess, do. Nobody uses Newton's law to write this. Okay, so that was Lagrange. And the most remarkable thing, I think, is the next thing, is that it was realized, he realized that the motions are shortest paths in space-time in a certain sense. So here is a variational formulation. So far, we formulated mechanics in terms of differential equation, whether Newton's or Euler-Lagrange's. But the hidden truth is that there is a deeper variational formulation. Instead of writing a differential equation, we can say, what is it that the physical motion actually does? And so to see the whole picture, we really need to think of time geometrically also. We are just watching the thing move. Physical approach is inadequate. We have to look at position and time. So let me just look at x as one-dimensional. So it's, everything I say, of course, is independent of the number of dimensions, but let's just think for simplicity of x is just a point in the line. Here's position of the particle. And as the particle moves, we draw its graph. So it starts at some point x naught at time t naught, and it moves, maybe there is a spring involved or whatever, and it ends at point x1 at time t1. So let's consider an actual motion. That motion is described by a graph, t naught, t1, and this is x1, and this is x naught, right? So the actual motion is, geometrically speaking, a curve in the xt plane. And we can introduce the cost for not just the actual, so this is the actual motion, but I can just take any curve connecting these points. So let's call this curve x of t with a tilde. So, and I can call the cost of this the length, quote unquote, of this curve. It's called the action as the integral of the Lagrangian along this curve. So in other words, we plug the curve, the coordinate x and x dot. So it's a simple recipe. We take with the Lagrangian, we take any curve and we compute the cost of this curve. And the amazing thing is that the actual motion makes this cost minimal, or, well, let's say it's true if the times are not too far apart. I don't want to go into the, so this is the theorem that if I will just say that if S of X, I use brackets to indicate that S is a scalar, right? It's just some number, but X is a curve. So the input is the curve and the output is a number. So it's a functional, it's a function on a curve. So if S of X is minimal, for any, if this is the shortest path between these 2 points are fixed once and for all. and we're looking for different paths connecting them. And if a particular path X here is shorter in the sense of this number than any other path connecting these points, then it's a true motion. Then it satisfies the Euler-Lagrange equation. Then X satisfies Euler-Lagrange equation, this one. Should I describe why this is true?
Can I make a question?
Sure.
I know this as Hamilton's principle, so I was wondering why Hamilton, since it's due to Lagrange.
I don't know. This subject is full of these things. I didn't do a thorough historical search, but
okay, it was just a curiosity.
I'm absolutely convinced that Lagrange knew it because
oh yeah, okay.
He would have been. He was a genius. I don't know, but you're right. It's called Hamilton's principle.
Yeah.
And the same thing happens with Maupertuis's principle. Maupertuis's principle says that if you prescribe the energy and then I throw a piece of chalk from one hand to the other, but the energy, then this parabola is shortest in the sense of that of all the motions with this energy, it gives the shortest integral of distance weighed with velocity, whatever. Anyway, so Maupertuis, it should not be called Maupertuis. It's actually Koenig who did it way before Maupertuis, I think like 25 years, if not more, before Maupertuis. And then I read I took the trouble, I opened the article of Maupertuis, and I think he has a mistake, which is basically he puts something in the denominator instead of numerator. And as far as I could tell, he did nothing. I don't know. But Euler at the same time wrote a beautiful article where everything is crystal clear, and he proves this least action principle of Maupertuis for some examples for the celestial motion. And
could you show this the proof and give reference to the article? Would be nice for the students also.
Yes, actually, this I wrote a text on classical mechanics, and there is this. I don't remember if I put Maupertuis's reference there.
Oh, you can give also your text, of course.
Yeah, I can send the text if anybody asks me. I will be happy to.
Yeah, I will. I'm asking.
Yeah, okay, and the proof. So the proof is basically a verbatim repetition of the proof that from vector calculus that a function of n variables has a minimum. If a function has a minimum, then gradient is 0 at that point. So maybe I'll repeat that proof and I'll show. So let's say if we have a function of 3 variables, let's say n, to me, if you know 3, then it's n is enough. I mean, 3 is enough. So fx, let's say f, that's a function of x is a vector. And let's say it's a minimum. Then gradient is 0 at f of x naught. So I just want to say that one doesn't have to, one can mimic this proof. So how do we prove it? So we have, geometrically speaking, here is the point x naught where in space where the scalar function takes its minimum. So f is a real valued function. So we take any vector c and restrict our function to the straight line. And so we consider, in other words, f of x naught plus epsilon c, where epsilon is the parameter along this straight line. And when epsilon equals to 0, we are here. Here, the epsilon is basically distance. And when epsilon is 0, this function of one variable now has a minimum. So in other words, the derivative with respect to epsilon at epsilon 0 vanishes. That's just from functions of one variable. And the chain rule says it's the gradient of f evaluated x naught times the derivative of this stuff with respect to epsilon, that's xi, so dotted with xi, that's 0. And so this is true for any vector xi, and therefore the only way this dot product can vanish is that the gradient is 0. So now a verbatim copy of this proof is for the for S. So S is like our F, and X is like our X in the finite dimensional case. So how do we do this? So we take S. Yeah, I should draw C. So again, a self-contained picture. So here's T, X, here's the minimizer. So this is X of T for which, so this is like X naught of T, right? So maybe I should call it X naught. That's the curve for which gives us the smallest possible value of this integral. And we want to change it, just like we change this vector here, we want to change the curve. So we add to it a function which vanishes at the end because we cannot move the end. So let's say C of T is 0 at T naught and T1. And arbitrary otherwise. So Xi is an arbitrary function which only vanishes at the endpoints. And we look at the function x naught plus Xi of T. So that's this fat thing, right? We evaluate our integral at that function, and we multiply this by epsilon, right? Small epsilon. So I want to take derivative by epsilon with epsilon equal to 0. You see, it's an exact copy of what we had done here. So I need to differentiate by epsilon that integral into which we insert x naught plus, do you mind if I don't write t? So it's x naught plus epsilon xi and x naught dot plus epsilon xi dot dt, right? And so we differentiate by epsilon inside the integral, so we get integral from t naught to t1. L must be differentiated with respect to the first variable, which I denote by L sub x. So we differentiate L by this, and then we differentiate this by epsilon. So all that's left is xi. And we do the same thing with the second entry. So we differentiate this L with respect to the second variable, which we call L sub x dot. And we differentiate this by epsilon, which is xi dot. Okay, so we're almost done, but you see, when we did this finite dimensional differentiation, we had a dot product of something with xi. Here we don't quite have that because this annoying derivative above xi is happening. So we need to get rid of it. And we do it by integrating by parts, the second term. So what do? We just move the derivative onto this and pay with a minus sign. So this is integral. The first term doesn't change. The second we paid with a minus sign, derivative by t of L sub x dot. And that is now times xi. But when we integrate by parts, we also have to remove the derivative, take this outside the integral. So we take L sub x dot times xi, and change it, C from T0 to T1. But C is 0 at the ends, because we didn't want to change our function by adding C. So that thing is 0. And because X, this derivative is 0, right? Because just like it was here, because X0 is a minimum. So this is 0. And it is 0 whatever Xi we take, any function Xi with vanishing. And the only way this can be 0 is the stuff in parentheses is 0, and that's the proof. So this is for all Xi, and therefore Lx minus ddt. So that's the proof that if the function is minimizing, then it must satisfy the Euler-Lagrange equation. Euler was a really very generous person. He actually figured out this solution by a different method. And what I showed is Lagrange's, I believe. And Euler was very willing to give Lagrange all the credits. He was not only a genius, but a nice guy. Okay, so this is one of the most amazing things, I think, because it seems like a divine intervention that how can a mechanical particle know of all the possible paths between the endpoints? How does it know to choose the smallest? I mean, after all, if you choose the smallest path, don't you have to know about the alternative paths? You cannot choose the best solution without knowing anything about other motions, right? So it's one of the most amazing things. And what really always amazed me is that I have not seen any books on mechanics, on classical mechanics, which say that this, in the whole book, this is the most amazing thing, and they pass in silence the explanation of this thing. It's kind of, maybe because it's not part of the subject, I don't know, but it is the foundation. And so I can recommend Feynman's QED, where this is kind of explained to a large extent. But what amazes, what is really interesting is that if somebody asked this question in a very, very persistent way, I believe that quantum mechanics could have been discovered like 50 years earlier than it was. Because what is the reason for this particle knowing in optics? It's the same thing happens, right? The light follows Fermat's principle. The light picks the path of least time. And it's not because there is divine intervention, as people used to think, but it's because the rays have wave nature. So it's, if you take the path, the shortest path, the quickest path for light, and look at the paths that are near it, and you look at how many waves fit into that nearby path, it's because it's a stationary path. Nearby paths have almost the same number of waves. In other words, the point I'm making is that the signal that arrives along the nearby, the paths that are close to the shortest one, arrive in sync, so they don't cancel each other. Whereas if you choose a different path, and the light does follow that path too, but the nearby path cancels what this brings. So they simply cancel. The ones that don't cancel travel along the quickest time. And the only, the only explanation for the mechanics, it must have been the same thing. Why there must also be some hidden waves which cancel, and which explain why the shortest path is observed, and that's quantum mechanics. So, in other words, I suspect that some people must have thought that there's got to be a wave nature behind all this, but maybe they were embarrassed to say anything so that they wouldn't be considered quacks or something like that. And unfortunately took it to their graves. I probably should stop. Is that?
We start a little bit later.
Okay,
so
I can. Yeah, no, I have. I remember how Charlie Conley, when he was alive, he said, "If you have any questions, please don't ask because I have too much to say." But okay, so maybe I'll describe the Hamiltonian formulation. That maybe would be a reasonable place to finish. So Hamilton, then I guess what 50 years after Lagrange, Hamilton made the formulation. So so you start with the Lagrangian. So there is another very nice way to write equations of motion besides the Euler-Lagrange. So you start with the Lagrangian, which encodes, like I said, all the information, because the mass of the system, all the geometry, everything is sitting in this one function, the force field. And then you treat this first as a function of, again, two independent variables. So I'll call it L of X and V so as not to confuse. So V is suggestive, but V is independent of X, it's not yet a function of time. And we define a new function well, define a new variable P as the derivative of L with respect to V. Sorry, this is not very else. Differentiate with respect to V and define a function of P. X is just a parameter as V times L sub V minus L of X and V is meant to be, I want these to be independent variables. So V is a function of P and also of X by virtue of this definition, right? So V and P are now related to each other, and I choose to take P as independent and V is the slave of P. Okay, so this right away is, why do you do this? One can see that it works in a simple case. Well, what works? I mean, I didn't say what works, sorry. So this is the definition, and then the theorem says that the Euler-Lagrange equation, that's a second order equation for X, right? Because it involves two derivatives of X. So this equation is equivalent via this definition to a beautiful system X dot equals to H differentiated with respect to P and P dot. So it's a much more beautiful, well, system. It's so first of all, I want to say at this stage, it's totally unmotivated. It's not clear, of course, why do you introduce H and why do you introduce P like this? And in the second lecture, I will say that if you just have one starting point and use the idea of Archimedes, basically, then all of this stuff comes out like from the horn of plenty. You suddenly also, as an added benefit, you see a geometrical meaning of P, a geometrical meaning of H. You see why the phase flow of the Hamiltonian system is area preserving, as though, even though it's a trivial fact to prove, but what's not trivial is to see this before you even write these equations. It's totally unclear, right? I mean, how would you predict that the Hamiltonian system preserves area flow, the phase volume, before even writing the equations. So that's, but maybe I will just say very quickly a geometrical meaning of, even though it's not explaining why you define P and H, but to give a geometrical meaning of these. So here is a really simple picture. So interpret L, without loss of generality, let's call V, and this is area P. And let's interpret L of V. X is the parameter, I don't even write it here, right? It should be L of X and V, but right now I leave it out. So interpret L of V is the area under the curve. So, okay, and then H, and P. So you see, I interpret L as this area. So what does that mean? This picture geometrically. So if I differentiate the area with respect to V, I get this height. You see, that's the same equation. If I ask what's the area of the rectangle, it's V times P equals to L plus H. And that's exactly this. And now kind of a religious proof, so to speak. If we have P equals to L sub V, but the picture is completely symmetric, so we know it's got to be true that the other way around is also correct. That means H sub P must be V. Okay, and another fun exercise to show that L sub X, now I recall that there is a parameter X. So far, this picture involves, I didn't care that there is X in there. But let's say L depends on X and therefore everything else does as well as a parameter. I could call it lambda. And the question is to show that L sub X plus I'll write it symmetrically, H sub X is 0. And the hint is that if you change X a little bit, you know, the curve changes a little bit. And whatever it takes away from one area, it gives to the other. So the sum is unchanged. Okay, so I will. Okay, and the last thing I wanted to say was, so you see, every additional discovery. So here's one side benefit that is kind of hard to see from Lagrange's formulation, but from Hamilton's equations, that X dot is H sub P and P dot is minus H sub X. What it really says is, in the plane at least, it says that if we look at the level curves of H, then the gradient H is a function of X and P, right? And this is the gradient, which means partial by X, partial by P. And X dot, you see, H sub P minus H sub X is the orthogonal vector. So in other words, it's an amazing thing that every mechanical system like that is, well, at least with one dimension, but this is true for any dimension. It's like a gradient flow, but in the perpendicular direction. And from this, it's not hard to see, or just by calculation, that the flow preserves area. So in other words, if we take a bunch of points at time 0 and let it flow, whatever h is, the area of that blob is not going to change. So because divergence of this vector field is 0. So divergence, if you recall, it's the partial derivative with respect to the first variable of the first coordinate plus partial derivative with respect to the second variable of the second coordinate. And so this is just h differentiated by p and then by x minus h differentiated by x and then by p, and that's 0. So divergence is 0. That means that the flow is incompressible. Again, it's a calculation, but why? This always puzzled me. And so I want to describe next time why. How can you see all these things without calculation? Oh, and another thing I just wanted to mention when I was discussing Lagrangian conservation of energy for the, well, for the Hamiltonian, Hamiltonian turns out to be the total energy. H turns out to be the kinetic plus potential energy. And the Hamiltonian is preserved. You can see it from this picture right away without calculation, right? Because if the motion is tangent to the level curve, then the motion stays on the level curve, which means h is constant along solution. But for the Lagrangian, how does the energy look like in the Lagrangian? It turns out that the energy for the Lagrangian is this x dot L Lagrangian differentiated by x dot minus L. So that's a constant along solutions. Again, the standard proof is by calculation. You can just take a derivative. Let's just quickly do it. Say take derivative and show it doesn't change, that it's constant. So it's first we take a derivative of the first guy times Lx dot plus x dot times the derivative of L. So that came from here. Plus, oh, sorry, minus the derivative of L with respect to time. So this is L sub x times x dot, right? Minus L differentiated with respect to x dot, because L has x and x dot in it, times x double dot. Okay, so these two cancel. And these two are x dot times the Euler-Lagrange expression, which is 0. So again, it's a totally unilluminating proof. Why is it true? We see it's true, but we don't understand why, and we don't understand why, at least I didn't. Why do we form this expression? You see, it's basically the Hamiltonian, right? I mean, it's how we define the Hamiltonian. VLV minus L. You see, V times LV minus L. But why? I think so. Yeah. For those who haven't seen it, this is the area preservation is Liouville's theorem. It says that if the divergence of the vector field is 0, then the flow of the vector field is incompressible. It preserves volume. Okay, I probably should stop. Unless you want me to continue, but I don't want to over.
Yeah, no, that's okay. So no, it's great. Thank you. Very nice, very pedagogical. And you're right. There are a lot of things that we're used to see that are satisfied, but it seems like a magic, you know, why this is true. You're very much right.
Mhm.
To me also why Newton's law are true, you know, it took me a while to understand there are axioms, you know. So
Why is what? I'm sorry, I didn't catch.
the Newton's law are axioms, you know, when I
Oh,
was when I was a physics student, I tried to, you know, understand where they come from. I should prove this, you know, and just recently, more recently, I understood there are axioms, and they might depend on the geometry of the space and so on, but they are axioms, you know. So, but
yes.
and then they're good postulated for mechanics, but they're not taught as that. And I think for first year student is a little bit confusing, you know, because at least to me, you know, because I tried to figure out where I should derive this from. So yeah, there are a lot of things that we should
Yeah, for example, where does the difference of Lagrangian kinetic and why is it difference? Why the Lagrangian difference of kinetic and potential energy? I read this. I will try to find the reference. But it's basically I'm not going to go into any of the details. But basically, it comes again from another axiom, but at least it's a simpler one. It's from apparently Einstein figured it out. It's if you look at the particle and you look at this integral of E dt, but t has to be in the reference frame of the person of the particle. And when you translate it into the observer's frame, E is, you know, mc squared, and m is a little bit bigger because he's moving fast, because he's moving. And so that's E. And t is a little different because he's moving and his time is different. And so when one translates it to the observer's frame, the leading order term turns out to be the Lagrangian. In other words, this integral is some constant, which may be rest mass times speed of light. But the next term is the difference of kinetic and potential energy. So it's not, I guess in the end, something has to be assumed based on experience, but at least this thing looks simpler than until I guess you start deciphering what E and T are.
And I like your geometric drawing about L and H. the geometric.
Yeah, that's a nice picture that has everything. There is a standard definition of in Arnold's book, it's defined maybe kind of if one draws L as a function of V. So this is the graph of L of V. X is just a parameter. And then one draws a straight line with slope P and looks at the tangent that's parallel to that slope. And then this is L and this is H. So from this one also sees that, you know, this is V, and so the height H plus L is the run, which is V times the slope, which is P, right? The height is the X times the slope. That's kind of X times the slope. So that's, and so I guess one can think of V as independent, or can think of P as independent. So as you know, but I think this is kind of a little bit easier to see.
Yes, indeed, I knew this explanation. I was aware of the latter one, but not of your first, and I find it very nice, very easy, much easier.
Yeah, it's kind of clear, symmetric from from this one. I don't see the symmetry.
Yeah, I found it very easy, much easier to understand. Yeah, I agree with you.
By the way, with this subject, it's really funny how I just saw recently an article by Einstein where he derives Jacobi's theorem about how to integrate a Hamiltonian system using the Hamilton-Jacobi equation, and he says that there is this standard thing, right? But he says, however, I do not know of a natural way free of surprising tricks of the trade where one begins at A and ends with B. So basically, even Einstein couldn't understand. And the same thing, Jacobi said the same about the Mappertui principle. He said something that this principle is described in such a way that it's not a verbatim thing, no, in such a way that basically that he could not understand. That was explained, sorry, that was explained in textbooks, even in the best ones, and he quotes some famous names, in such a way as not to be understood, at least not by me, he said.
Thank you very much. This wonderful lecture. So before I forget, let's thank Mark for his wonderful lecture. So you can all open.
I have a question.
Yeah, then we can have questions, but otherwise we forgot to thank the speaker. So let's thank the speaker, please. So we can.
Thank you very much.
So open the question, please.
Yeah. Did Euler and Lagrange exchange letters during this period of the variational calculus?
Yes, I don't know the details much, but I know that Lagrange, I think, sent Euler his derivation that, and Euler, I don't know I only remember that Euler was very generous and kind of was willing to give Lagrange all the credit. I should read more history, I think.
But we would like to have your notes about mechanics, the one you wrote. The one. Okay.
Yeah, I can send you the old, I mean, it came out as a book, but I can send you the file that is slightly less polished than the book itself, but it has an advantage of being free.
Yes. So other question from, you can ask question, or we can ask question at the beginning of the next lecture if people prefer. We have something. Okay, so Adriano, you can say if you can speak. Adriano is a professor at our university. Adriano Cortes, please. Adriano, you can say.
Good afternoon, Professor Mark. Wow, so what was really an enlightened class. Many thanks.
Oh,
it was really good.
Thank you.
Yeah, it's one of the old class like we used to in presential time, you know, where people can take the time to think about it and think written. So very nice. So okay,
I really appreciate the historic notes and comments. Yeah. It's raining in Rio, so it's I don't know, I think it was a class that matched with the day learning. It was really, I agree with my colleague.
Well, I would switch places with you. It's getting colder and yeah. Yeah,
for us it's quite cold because in Rio, if it's below 20 degrees Celsius, not Fahrenheit, it's already quite cold. I have a sweater and a blazer, but I understand. Yeah, it's getting winter now. It's starting the winter in Pennsylvania.
Yeah. I have some distant cousins in Rio, actually.
Oh, really? Well, nice.
Professor,